SolidWorks simulation, specifically large model best practices. So this presentation is going to be split up into two main phases or categories. One is to kind of introduce to you all and let you know about some basic concepts that I want you to be aware of for when you're working with larger models in simulation. And then the second phase is going to be me showing you some SolidWorks tips and tricks examples of some of these utilities that maybe I'll allude to, and then show you how it actually works in SolidWorks after just after I talk about it, basically. If you haven't spoken to me, I just want to introduce myself. My name is Enrique Garcia. I'm one of the simulation specialists at Go Engineer. I've been working in the reseller channel for 16 years at this point. Working in technical training for 16 years, simulation training specifically for 15 years. Procured quite a bit of certifications over the years as well. So if you have questions about them, so I can give you some tips and tricks. Also, we have in-state here, local in Arizona, we have my colleague Joseph Richter, who some of you guys know. He is the simulation, he is the certification guru of the company. So you guys have some pretty good resources with us here in town. Also, I'm a bit of a tinker. I like to take things apart, see how they work, put them back together. Took apart my dad's computer in when I was 12 years old. And he freaked out. He came in and I got in trouble. But I put it back together and it was working. I upgraded the sound card, so that kind of shows my age a little bit, right? So sound cards are no longer a thing. But yeah, just been playing with that. I've been learning how to do watchmaking in recent years, taking apart watches, mechanical watches. I buy them on eBay, restore them, find the spare parts online, and lubrication. It's like working on on an engine, like on the cars. There's drivetrains. There's a whole thing. It's really fun. So been doing that for a good couple of years now, 2 years. It's been a lot of fun. I've always been in like the customer service industry. My family owns a restaurant, a local business in town called Miracle Mile Deli. So yeah, it's on 16th Street and Campbell in Phoenix. So best restaurant in town, Miracle Mile Deli.
It's famous.
Oh, nice. Yeah, family owned. So I've been working there since I was 12, 13. So child labor is real. So. But yeah, so a passion of mine is training and teaching. I started teaching high school band as a woodwind instructor and did that in college and a little bit after college. And so I definitely enjoy mentoring students. I'm mentoring an ASU East campus student at the moment and just giving them advice. It's a little bit about myself. Here is a slide about the three major simulation softwares that participates or lives inside of the SolidWorks ecosystem. The one that we're going to be focusing on is our FEA tool, SolidWorks Simulation, which is in the middle there. It's broken up into the 3 tiers. If you have questions, definitely ask me. But we'll move on here in a moment. We have SolidWorks Plastics, which is our thermoplastic injection simulation software. That's just another add-in away. And then we have our computational fluid dynamics software, SolidWorks Flow Simulation, and a couple of modules, and that's meant to be able to simulate, model fluid mechanics, heat transfer with fluid mechanics. So it's built for that all day long. So that's some of the tools we have in the software. This is the agenda that I have for our presentation for us today. Like I mentioned, it's broken down into 2 main categories: our best practices or concepts we're going to be introducing to you all, things like pre-processing, some strategy for simulation modeling, and just some general stuff, some tips for that as well. And then the tips and tricks and introduction to some utilities we're going to be using and just showing you about. So let's talk about the first concept here. This is pre-processing your large models. This is something that, actually, let me ask, I guess people that are here, who here is a simulation user? Just raise your hand. Anybody use simulation? Okay, a couple of y'all, all right. So very good. So for those of you that are interested or maybe are going to be using it in the future, this is, all of us that have been using simulation, we've all gone through the school of hard knocks. We know what not to do. So this is a little bit of that here, which is what we call pre-processing your models. So if you have a CAD model, sometimes if it's ready to go, it's ready for production, it has all of the detail, right? So it's up to us as analysts to go in and to simplify the model, getting it ready for simulation. You never want to take a model with all the detail, add all the constraints, boundary conditions, adding all the calculation nodes. You're gonna have a bad time. So there's gonna be a lot of errors that you're gonna have to deal with. And so part of this is what we call pre-processing in models. And there are three ways we can do that before even touching simulation. The first way is called simplification, or basically defeaturing your models, going in and deleting things that maybe you think aren't going to be participating in the response of the model, or suppressing features. The next thing is going to be what we call model idealization. Model idealization is representing more complex geometry with simpler geometry. Simple as that. The last thing to consider is model cleanup. So we'll talk a little bit more about these here in this next segment. First is the simplification or defeaturing of your design. So if you are the CAD model and the simulation person, then this is not that big of a deal. You can maybe, if you're building something, you typically build the main bones of it, the skeleton first, right? And then you can do some quick structural testing on that to see if you're pointing in the right direction. And that is the meal ticket of this tool, ladies and gentlemen, is having it built into the SolidWorks ecosystem so you can just check it real quick, move on, and start continuing to develop your design. But if you don't do that, what you can do, if you have the model already pre-done, simplify it. You can do that in two ways. You can do that by maybe making a separate configuration. Question, who here uses configurations in SolidWorks? Raise your hands. Awesome. Okay, perfect. All right, so you can very easily make a configuration, call it simplified or FEA, something like that. And then on that configuration, go in and start to suppress different features in there so that they only exist in the full-on model, the default config. And then for this one, they are no longer in there. If you're doing this retroactively, it is painful because you're having to go into the part level and do that, then sub-assemblies, then top-level assemblies, right? So a good practice is, as you're designing your CAD models, you make up a part file, make a quick simplified config, and start to suppress the small detail-oriented features, all the small little holes and things of that nature. This way, all you have to do is when you're ready to do simulation, just go top level and say FEA simplified and start working on that. Another approach, especially if you're doing consulting work or if you're working on a live model, you want to be a little careful with that. So what you can do is use SolidWorks Pack and Go to make a copy of that family of files. So then this way you can apply a little prefix or a suffix. I like to call it FEA underscore, something to ensure that you're going to give yourself file names for all of these separate system of files, and then go to town on that. Go in, suppress things, delete things to your heart's content. So that's the approach that we like to take with simulation and simplification. The next idea with pre-processing your models is the concept of idealization. And if you look there on my slide, the top right corner, we have just a heat sink, and we're just replacing it with something simpler, something with less features in the model. You can do that all day long with the different individual components, or we have some models or features in simulation where we can replace fasteners, things from a MasterCard. You can have in your model, just we can get rid of those and put in features that represent those same structures. So we have nice translation of forces going through. We even have some rudimentary axial forces, shear forces, et cetera, that you can get from that in an ideal situation. Another idea of idealization is using additional what we call elements in our simulation. When you're running simulations, you basically apply calculation nodes throughout your entire model. These calculation nodes can be grouped into individual shapes. And so we can represent thick components with a shell, what we call 2D or shell elements, and tell it and assign what the thickness is of that gauge of whatever sheet metal part you're using. Same thing goes with weldment applications. If you have structural members, instead of going in and adding all the calculation nodes for all the different bends and things of the profile, go in and use a beam element, and the software will sample what that profile is and apply it throughout the entire length of a beam element. So these are ways to simplify and save on calculation resource. And the last thing with regards to pre-processing your model is model cleanup. If you're working and you're importing geometry, this is especially if you're importing geometry from another CAD system or a different modeling kernel where translation error can happen, then you may have to go in and run what we call import diagnostics utility, just under the insert menu under evaluate. Pretty useful, pretty robust tool. It's always a work in progress. We're always trying to improve it. You basically will go in and you can select an item, and it'll tell you under the tooltip what's going on with it. If you're having an issue with like an overlapping face like you see there, or edges don't meet up to close and knit different surfaces, and you can attempt to heal all and it'll try to fix it, and I would say it fixes 95% of all the issues. But that's import diagnostics utility. Another tool we have is quite old. It's been there for, gosh, as long as I can remember. It's called check entity. And it's under the insert menu, also under evaluate. And this is an interrogation only tool. And it's meant to be able to show you where invalid surfaces are or edges. And again, it's only there to show you where the item is so that you can fix it with using your own SolidWorks knowledge, whether that's surfacing or just a prismatic design. But yeah, be prepared to fix models so that you have an easier time in simulation. The other tip I have for you with simulation, if you are going to be using it, look for interferences. If when you're applying calculation nodes, if you have two bodies that are occupying the same volume, it does not know how to assign calculation nodes within the same volume, so it's going to give you some error messages. The mesher is a bit robust. It will try to separate things with some tolerance features, but ultimately it's up to us to go in and resolve any interferences. Any questions on that section? All right, so the next one, it's a little bit more straightforward. This is talking about choosing an approach to your larger simulation models. Again, if you're doing models with like 10, 12 components, you're probably okay. But if you're doing parts with models with 20, 80 different components, you may want to look at one of these approaches. So the main thing before you pick an approach is to look at the area of the model of interest, figure out what that is. In this case, I have a scaffolding, and I've decided maybe those brackets that attach the top level of the scaffolding is my area of interest. So we have two approaches for this we can take. The more traditional or classical approach is going to the main component of interest or the main components of interest, and then starting with the simulation small, with very, very simply with the one part file, and then slowly start to grow out and include additional components until you're satisfied. The other approach is the opposite. Start very, very large with all of your model, maybe simplify the model a bit, and then you can zoom in as a second phase into that area and inject the individual components with the response. But yeah, the first part is again, start simple. This is the classic approach. Start simple with the main component of interest. In this case, maybe I've taken those 5 components of the scaffolding. I can split them up using SolidWorks features, like the split part function is pretty amazing. I use that quite a bit. If you're splitting components in simulation, even though they split, whenever you attach them, you have the ability to have a continuous mesh and have it kind of arm wave ignore that boundary. So we have some flexibility, even if you split the model quite a bit. So you can split the model up here, then you can run the analysis on that smaller portion of the model, get some results that you think are going to be okay or ballpark, and then slowly incorporate additional components like you see on the third screenshot there after the second arrow. Continually add different components until you're satisfied with the result. The other approach is going to be starting with a large model, and maybe even simplify it a bit, maybe keep the areas of interest as geometrically perfect as possible, as accurate as possible. In this case, maybe those brackets are going to be left alone, but then run the analysis, and then we can inject the response at those boundaries of where I've cut and I've zoomed into my model. I can inject the response of the larger study's response into this smaller response as like a two-phase kind of approach. So this idea here of zooming in from the larger model into that smaller little area there This is called submodeling. I'm going to show you the workflow for that here in a couple of minutes. But that's the idea. Just again, think about how you're going to be approaching your model's design in the end. Any questions on simulation approaches? So the third major question is, or concept I want to introduce to you all is the size of your calculations. In SolidWorks simulation, your computer's RAM is what I like to call your computer's computational currency. The more RAM you have, the more degrees of freedom you can calculate. Basically, the larger the calculation is that you can calculate for your simulations. Now, who here has run into this pop-up that I've used simulation before? Model problem's too large to run this study. It's a little bit annoying. So I'm going to give you some tips maybe of how you can maybe approach something and maybe not so that you don't bite off more than you can chew, basically, with your computer's resources. So this is the $1,000,000 question I get asked whenever I talk to new customers or that they want to buy simulation, or maybe they're a seasoned customer and they're going to buy just a pretty super big computer, right, dedicated to simulation. They ask me, hey man, how much RAM do I need for my simulation? And the question is that's the key question, right? You don't know. There's I would say we need more information. I do have some general tips I'll share with you at the end if you're just starting off, but if you want a customized answer, I can't tell you with hey, this is the model I'm using. No, it depends on a lot of things. It depends on the study type that you're wanting to run. If you're doing a static study, if you're doing a thermal study or a nonlinear study, that's going to take a lot more resources than a thermal study or a linear study. The elements that you're going to be running and sampling when you apply your calculation nodes for your model to match the model, how those elements, how those calculation nodes group up can affect how much RAM and resources I need to calculate the simulation. Also, the simulation approach, are you starting small and then growing out? Are you wanting to do the big picture and then zoom in? That's going to be important. And overall computer usage, right? What are the other softwares you're running, right? If you're running Zoom, right, is that going to play wrong with the software? Or if you're running Microsoft Outlook, right? That's a resource hog, I'm telling you. I use the web app to try to lighten up my load when I'm doing simulations. That helps a bit. iTunes, actually, who even uses iTunes anymore? But yeah, so other computer softwares are going to be important to how much RAM you're going to need. So the number of RAM, this is the key here is equal to how many degrees of freedom. Those things are all equally related, and that's going to tell you the size of your calculation. So to find out ultimately how much RAM we need for my machine, we need to figure out how many degrees of freedom I'm going to be using on a very characteristic model that I'm be running a model on, and so I can know the size. And then at that point, I need to figure out what kind of study I'm running and how many calculation nodes. I'll be showing you how you can look that up here in a moment. And what is the predominant amount of element types that we're running. All right, so let's talk about number of degrees of freedom. How do we calculate that? So to get that, we can look at the model, the simulation study. We can right-click on the results folder, and it'll give it to you, right? But that's fine if you have a model that's easy to run, right? But the idea is if you have a model that's large, it's going to take a couple of hours to run, you want to know this information before you run the study, right? So not after it's been completed. So if you wanted to find that out, just for future reference, boom, there you go. Right-click results, go to solver messages, and you get the number of degrees of freedom. So let's figure out how we can estimate that value before running a large-scale simulation. So each calculation node generated by the mesher has the potential of running up to 6 different degrees of freedom. So it depends on the element type as to whether we're going to do 6 different degrees of freedom per calculation node or less. This is the breakdown. So if you're doing a lot of prismatic modeling, a lot of blocky components where you're using solid elements, then you're going to be running 3 degrees of freedom for each calculation node. If you are using weldment applications and you're using beam elements or if you're using 2D shell elements, you're going to be having to calculate 6 degrees of freedom for each of those individual nodes. So just I'll leave that as a reference. So here's how you can quickly estimate how many nodes you'll have. So you'll go into the model, you're meshing it after you finish running the setting up the study. Before running it, you're going to right-click on the mesh folder. You're going to click details. In the meshing details window, you're going to see the total number of nodes there that's been blocked there in red. So we're going to take that number of nodes, and you're going to go into your parts folder in your simulation design tree there, and you're going to see simulation in SolidWorks is great for giving you a lot of good visual feedback, right? They give you right-click feedback, colors, icon changes are a little subtle, but you can still see. Here in my parts folder, we can see the predominant type of elements that we're going to be working with are going to be beam elements and shell elements. We may have maybe about 3 or 4 that are solids, but we know now the predominant element type is shells and beams. And those gives us 6 degrees of freedom per calculation node. So to find out how many degrees of freedom roughly, just multiply the number of calculation nodes there, the 22,929 by 6, we get 137,000 roughly. So that gives us a better understanding of the size of the model. So we'll tell you how that equates to an amount of RAM in a moment. But if you look here at the solver messages, I went ahead and meshed it and ran this. And we can see that the exact number of degrees of freedom are 136,000.7. And so yeah, I was in the ballpark, right? So pretty close enough for jazz. But again, so how much RAM now do I need? I keep getting that same question, right? I can tell you how big the calculation is, but now let's correlate that to amount of RAM on your machines. So a few years ago, I did a quick little study where I took a simple model and I looked at my task manager to see how much RAM I had. I'm trying to remember what other software I used. It was like it looked like it was made in Windows 98 or something. It was very rudimentary, but it gave you a raw visual of how much RAM is being used at the time on your machine in real time. I'm trying to remember the name. If I do, I'll let you guys know. But basically, I ran the study, and I basically found out that when I applied up to 200 degrees of freedom on my model, once I calculated that and I figured out when I ran the study with a linear study with, in this case, a linear study, so it gives us more calculation resources used. I kind of found out that about every 1 gigabyte of RAM, I used up 200,000 degrees of freedom for my calculation size. Now, I went ahead and added a little more mesh, or actually a lot more mesh, and I was able to double it to about 400,000 degrees of freedom. And I found that the amount of RAM allocation was a little bit more than 2 gigabytes at that point. And then I ran 800,000 degrees of freedom, and it wasn't quite linear of a response. It became a little more parabolic after that, after 3 or 4 more cycles. But overall, I could still kind of maybe guesstimate it as being a linear response. So in this case, if I had that 137,000 degrees of freedom, right? So if I divided that by 200,000, then I can figure out how much RAM I could use on my machine. So just divide your total degrees of freedom by 200,000, and that'll roughly give you how much RAM you're going to be using. Not exact, so you may want to go in and maybe adjust maybe 10%, a little bit more, just to be on the conservative side, especially if you're doing some professional consulting or something. It's always good to have a little bit of buffer. But yeah, the takeaways here is know the size of your calculations before running a large simulation study. If you don't, what happens once your RAM, your physical RAM, is used up, the software or Windows will actually go to your hard drive and allocate a section of your hard drive as RAM, and the speed is significantly slower. It's much faster now with flash drives and things, but flash memory, but flash hard drives, but it's still way slower than real RAM, onboard RAM. So you'll get You might get an out of core message, or you might get a message like you saw there about the solver the size was too large for the solver you're using. Um, so yeah, so know how much RAM you might need uh, for your machine. Uh, Also, if you're getting a new dedicated simulation computer, I have some asterisks there. Um, get as much as you possibly can, to be honest. If budget is a consideration, get the processor with the highest clocking speed, something that maybe can turbo boost, like an i7 Intel processor, something like that, and then fill out the rest of your budget with whatever RAM you can spare, because you can always upgrade that a lot easier than your processor. So go that route. Question.
Deal with the handles, like Windows sets standard handles. I don't even know what it's for, but when we were getting scanning, we were running out of handles, which was like sort of like a limitation on calculation. And then we talked to the company that helped us up, just type in, you go under all the settings, you type in a new number, which has to be like a variable, a certain number. And then it completely never ran out of memory after that.
Was it like virtual memory? Could that be what you're talking about?
It's called handles. I was wondering.
Handles. I personally haven't, no.
Setting that comes standard is fairly low, and then you can up. I don't know. It was like free.
Yeah. It might have been what they call virtual memory, like what I was talking about. Once you finish your physical RAM, there is a place in Windows where you can change that allocation size. So that could be that. And it may have been, it could be named handles, but it's been a year since I've worked with virtual memory. Yeah. Any other questions about such things? All right, last concept I want to touch on here is how are we doing on time? Uh, this is kind of I'm probably preaching to the choir, but budget your time for especially larger models, right? I came from SolidWorks tech support side. I started talking to all you fine people in when you're in the crux of your problems, right? So I can't tell you how many times I ran into a simulation user that maybe their problem could be the most complex design, right? But their issue was not their work. Their issue was not having enough time to get it done, right? So always budget. I wrote 15-20%. That might be a little bit heavy-handed, but at least 10% more time when you're trying to figure out setting up your study for troubleshooting alone. Here's a list of different issues that could happen that could cause you to be troubleshooting in no particular order. All of these could cause a lot of headache, and it's not only you, right? That's causing the issue. Now you have to tell your bosses, your clients, right? You're gonna have to break the bad news to your clients or your colleagues as well. If you're falling behind now, they're gonna be waiting for you to finish your project. So again, I'm preaching to the choir on this, but it's like the best practice of save and save often in SolidWorks or any software, right? Same thing here. Just troubleshoot. Save some time for dedicating for troubleshooting. And if you have no problems, well, heck, you're a little bit ahead of the ball game of the curve there, and you can pass over that savings to your colleague and for moving forward with your projects. But yeah, that's all I have to say about that. So let's talk about some tools and utilities that we can use in simulation and SolidWorks to help you be more efficient at working with larger models in simulation. The first one is going to be submodeling. And this is that second approach that we talked about, where we start with a larger model with many components. We run this study with maybe a simplified version of it, or if you have the resources, run it with a larger model with a very coarse mesh, the least amount of calculation points possible so that the study doesn't take forever to run. Get a response of the design. Then you can go in and create what they call a submodeling study, where I can zoom in into either a component or a group of components, like you see there highlighted in blue on this screenshot. And then you can in this zoomed in study, you can then inject in the form of a displacement response the actual results from the previous larger study into the smaller one. And then with the smaller study, then start adding all the meshing details and all those computational resources, just go to town on that. So let me show you the workflow for that. It is really simple to use. And I'm going to use this model from the screenshots. Let me turn on my simulation add in here. And so the idea here with this submodeling workflow, it's a two-phase process for this. You start with what we like to call the parent study, or just the general larger study. And so I won't waste time setting anything up here. I've already done up a setup here for us. Let me turn on the config for that here real quick. And again, the workflow is assigning individual materials to all the parts, fixing the bottom feet, putting in some loads on the model, maybe a dead load, and so a couple of concentrated loads on the thing here. And then running the model, looking at what the displacement is or what is the overall response of the design. A good practice is to always animate your simulations. If you see parts flying out into space, then you have an interaction issue. So I call it my sanity check with these tools. I just quickly do a quick check displacement because it'll always show all elements at once. So I can quickly check to make sure nothing is fouling up in my setup. So that looks great. So now I want to go in and zoom in to the area of interest here, which is going to be this region here where we have my little my little bracket here and this little crossbar. That for me is the area of interest. So I'm going to go in and do up what they call this submodeling study and zoom into this area in using this tool. I'm going to right click at the very top of the simulation design tree, and I'm going to click on create submodeling study. This is going to tell you what the tool is and some of the limitations you want to avoid on certain section surfaces. You want to avoid certain interactions and virtual connectors and things of that nature. So I want to go in and it's going to give me a property manager on the left-hand side here. And now I can go in and checkbox the components I want to participate in this zoomed in study. Or I can just click them in the graphics area. I'm going to click on these 5 individual components that you see there. Once I click OK, this is the closest thing to a do my job button we have in simulation. It'll start a new simulation study, a static study. It'll go in and isolate those individual components, and it'll take the same setup from the parent study over to this new study with all the forces, and it'll also inject that displacement we saw earlier for the larger model. There was a bit of displacement in X, Y, and Z, and those are going to be put into these boundaries once I finish zooming into this model here. It takes a little bit of time. I've been asking for a little progress bar because it looks like it's just kind of freaking out at the moment. So we'll get a little progress bar at some point. But now we've zoomed into this model here. And in my study setup, I still have gravitational pull, and it's based off of the center of gravity of the whole model. But the nice thing, the convenient part here is that it takes the forces, all those live loads, that dead load, and it proportionally distributes that across whatever's left in my study. So it does that calculation for me. And then at that point, I can run the analysis. I can then maybe apply additional meshes on the model here. And I've already run this here so you can take a look at it just to save some time. So at this point, you're going to go to town, right, and apply a tighter mesh in the component of interest for me. It's going to be this bracket. And then I can look at some results and I can do some result convergence because I have a lot more resources available to me. So here's the mesh. So I just started with some preliminary mesh controls there. And then I can start to look at maybe what the stresses are in those areas and start to do some, just my due diligence with this. But that's submodeling, and this is a nice automated way for that second approach we talked about earlier. Any questions? Let's talk about another concept. This is an automated tool that we can use next. And this is going to be local interactions. We're automatically finding and applying local interactions. Now, when you're setting up a simulation study, going through and assigning these interactions, whether you're bonding components, letting them respect each other with friction, or assigning them to be free, that is one of the biggest bottlenecks we have in our simulation workflow. You want to make sure you see that being done, right? You don't want to leave it all to chance. There's a tool that will help you automate this to kind of speed things up a little bit. Let me show you how this works. And it's called automatically find local interactions. So for this, I'm going to start maybe, so this is the model I'm going to be maybe basing it off of, or this study. And if you look here under connections, under local connections, I have, I think I counted, it's about 25 or so different interactions. So I could do this manually and say, hey, take this face and take this other face on part B and make them contact and respect each other. I can do that for all of the coinciding surfaces, or I can do it with a little more of automation using the following. Let's say I start up a new simulation study here. And under the connections folder, I'm going to start by going into local interaction like I normally would. At the very top of my interaction category, switch the radio button to automatically find local interactions. This is going to allow you to have an options area where you can say, this is like the detection tool where I can say, hey, find contacting faces. In this case, if they are having no gaps, which is fine for me. If you model with gaps or a tolerance in mind of some sort, you can always type in what that clearance is going to be to automatically detect those face pairs. And down below in this blue box, I want to go in and add the top level assembly. And I'm going to click this find local interactions button to be able to detect all of my coinciding or touching face pairs. So now at this point, I can go in and interrogate all of those interacting face pairs. I can decide if some of them are no good, maybe I made a mistake. I can always hit the little red X to exclude or remove a face pair from the list. Down below, I can specify what kind of interaction I want. In this case, I want a contact interaction. I can specify, I don't have to worry about gap clearance because everything is assumed to be touching. I can put in a coefficient of friction if I want. But yeah, at that point, I can go in and select, maybe I can start on the top, select the component or the face pair. I can hit the little green plus sign and add that interaction, and I can keep going. I can do them one by one, which could help a little bit without having to come in and out of the property manager. You can do a shift select and grab them all and assign all 25 or so individual interactions in a fraction second. At that point, I can close the tool. I can go in and double check to see all my different interactions here. Maybe spot check them. It's always a best practice to look over anything you do, including the automated, especially the automated stuff that you do in simulation. But this helps you with a lot of redundant clicks using this automated approach. Any questions on the automatic interaction tool? All right. The next tool or utility is a way to automate the creation of virtual bolt connectors or fasteners in simulation. So this can be done on the fly. If you're already inside of a simulation study, you can activate this capability. Or if you're starting fresh, if you're doing a new simulation on the initial creation, there's a little checkbox I'll show you. And this will take toolbox fasteners. There's a little bit of metadata in there specifically for this, and it'll then translate to features in simulation to exclude the fastener from the simulation and add in place its own dedicated feature with the appropriate preload, shank and nut diameter, etc. This tool is only for simulation professional and premium. But let me show you how to use this tool. And actually, a quick question for the group here live: who here uses the toolbox in SolidWorks? Just to find out. All right, you y'all. Okay, I see a trend going to just using the faster car, right? Just be careful, right? The threads, a lot of detail there. So simplify those components for us. Let me show you how to use this tool. So we have in my model, the very bottom, they use smart fasteners, and we've added a couple of toolbox fasteners, some countersink screws and nuts to these two brackets down the back. So if I'm in the process of making a new simulation study, I can click here under the study type. I can say convert toolbox fasteners to bolt connectors. Simple as that. Click OK. You're going to create your new simulation study. It's going to give you a little feedback here of how many bolt connectors we've added. And in the appropriate area, we can see under connectors, we have a little group of all the individual virtualized features of a bolt. And these can be put in manually, of course. If you don't use Toolbox, you can manually specify the different references for the edges and the end faces, the shank and nut diameter, a preload, if you know what that could be, ballpark, you can pop that all in. But again, this is automating that for you if you're already using Toolbox. If you are maybe already made the study and you decided to do this after the fact, not a big deal. I can go to this other study I've made up earlier with y'all, and I can right click under the connections folder and also say Toolbox fasteners to bolts and bring in and replace those fasteners over as well. You can see the preview. Also under the parts folder, we have this auto-converted folder where I've excluded those CAD models, those Toolbox fasteners from the analysis. And then in place, we're now using the actual virtual connector you see there. So again, it's not, doesn't take very much for us to implement something like that. All right. How am I doing on time? I'm a little over, so apologies here. I have maybe another 4 or 5 minutes of info here. Perfect. The next capability I want to talk about was added in 2020. So right around where direct mesh editing was added that Dylan was talking about, we've added this capability called mixed meshing. So maybe it was the year of meshing for SolidWorks, but basically when you're running a simulation study, we have two modes that we can mesh our models with. We have what they call a draft quality mesh and a high quality mesh. The difference between those two is basically the amount of calculation nodes that take up each individual segment or element that you make. If you do a draft quality mesh, you're going to end up with less calculation nodes and hence less degrees of freedom and a quicker run time for your simulation. If you do high quality elements, you're going to add a lot more calculation nodes, maybe probably a little more accuracy because you have more detail in the area, but it's going to take a little longer to run. So before 2020, you could either do it all or nothing. You could either do draft quality or do a high quality mesh and take up your time. The problem with that is, or actually the solution now, if I go to SolidWorks here, is I can mix those draft quality elements and those high quality elements in two places. I can do them here under this parts folder, which means I can say, hey, maybe on the components that I want to see more detail to, I can make those high quality, and the ones that maybe aren't really participating in the response, make them draft quality. So you can mix this stuff. In most simulation studies in the software, I think with the exception of dynamic studies, buckling, thermal, nonlinear studies can mix and match individual quality types of your elements. The way you do this is quite simple. You just go in and maybe you select a couple of components, maybe another one there, right click and say apply draft quality mesh to all of the highlighted components. And trying to remember how to zoom in. I think I need to turn on the capability magnifier. Oh, sweet. I'll do that. So you can see here that some of these individual elements now have straight edges. Those are your draft quality elements. The ones that have the squiggle tetrahedron, those are the high quality elements, indicating that there's like a mid node or an inflection point there. But that's the idea. Let me zoom back out here. Perfect. So now that maybe I've kind of told it which ones to do high quality with, which ones to do draft quality with, I can now go in regular and mesh the model and apply these calculation nodes. And I can click OK. And now I can see some of the mesh color is going to be orange, and some of them will be like a dark blue or a navy blue. The orange represents draft quality elements, and the dark blue represents high quality elements. Another place you can kind of manage this is going to be in the regular mesh property manager under this new mesh quality tab. Just another way to kind of organize yourself, how you want to show everything. You can do everything high quality or do everything draft quality like before, or just pick and choose which ones you want to bring over and do it that way. And so that's mixed meshing and simulation. Any questions? All right, this is also for non-simulation users. Who here has ever worked with selection sets? Raise your hand. Oh man, I got a treat for you guys. So when you're working, especially with larger models, right? Not just simulation, but you're now going in, maybe you're applying fillets to a bunch of edges, right? Maybe it takes it's meticulous work, right? Selecting all the individual edges. Maybe you got 50 of these things are going in a bunch of nodes for some reason, and maybe you're at number 41 and you get confused, or you just mess it up, right? You got to start over. You got to clear selections, right? Delete clear selections and then start all over. It's a pain in the butt. So this is also a pain in the butt for simulation users as well when we're going and applying a force load and you're having to select all the faces, right? So we can use a SolidWorks tool called selection sets to kind of save and package those selections to reuse and reharvest them over and over again. Let me show you what I mean. So let me hide this mesh here. And so let's say I'm making a, everyone knows what intuitively what doing a force is, right? You select the force tool, and let's say I want to choose maybe all of these faces on the model on both sides. Maybe I want to do something, maybe that's easy, but let's say I want to do something more complex and pick a bunch of faces and edges. So instead of doing that, I can have some pre-saved selection sets, and I can go into the little abbreviated SolidWorks design tree, expand selection sets, and then just pick what I want. Maybe the internal faces of the bolt connectors for whatever reason. I pick those, or maybe all the female and male yoke faces. Check that out. I'm adding so many faces all at once. 37, 42, 45. So 54 faces in maybe a couple of seconds. So these are pre-packaged entities, right? I can click OK and apply my force load. So that's the benefit of using this capability. Let me show you how to use it and manage it. This is, again, a SolidWorks feature. So I'm going to go back to the model tab on the lower left-hand corner there. And you're going to find a folder called selection sets. You're going to go in and you can make a new selection by maybe picking you can do the control select and pick a couple of faces, edges, combinations of points. And you're going to right click over one of those selections. And then in the right click menu, just choose new selection set. That's going to populate the selection sets folder with the new item in here. And yeah, now you have another place where you can just reharvest these faces or these entities over and over again with any feature you'd like and any of the tools in the ecosystem. If I wanted to add an additional face to it, I can click it, right click, and I can go to save selection and then pick the last selection that I've made, and I can add it to the list there. And that'll show up under that selection set area. And did I add that in? Maybe not, but then I can go in and manage them here as well. I can delete individual faces or edges or entities, and yeah, and manage them or delete the whole thing in this area here. Remove the whole selection set. But again, it's we've all been there, right? You're trying to select all these different edges, and it's painful. But that can help. Do it once, and you never have to do it again. Last one is going to be importing study features in simulation. So with simulation, let's say you're working on this large model, 200 parts, right? Huge simulation. And before you get there, you definitely spot check, right? You always maybe start simple with the one part file and start to graduate up to a subassembly and then the larger assembly. So you probably have already set up certain areas of your simulation already, right? So we can graduate or reharvest features down below at the part level, the subassembly level, and kick them up to the top level assembly and just bring them over. So if it's a force load we've already done or a mesh control, why the heck redo it, right? It's gonna much more human error that can be involved. So let me show you how you can graduate up and bring in or import these study features from lower level parts and assemblies. So for this model, I went into this bracket and I did up a simple static study, and I put in a force load, I think a mesh control, and some virtual fasteners of some sort. Just want to show you what that looks like. So this is the setup here. It's the force load, a little bolt group with some foundation bolts, and a mesh control. And so now I'm going to go on over to my top level assembly. I'm going to, I can use this existing study that I'm working on here. And let's say I go and I right click at the very top of that tree and I say import study features. This is going to give me the import study features window. and it's going to scrub through all of my subassemblies and parts. And if it sees that there's a simulation study with a feature that can use, it'll bold it out here. Like you see at the very bottom, it's kind of subtle on the projector, but it's the second to last line item, number 15. It detected that I have those features down at the lower level. Over there on the right-hand side, I can specify what study. I named it lower level study features just for convenience. But then I can decide what features I want to include and graduate up here. The meshes, it's fine. The force loads, virtual fasteners, all of that's good. All I have to do is hit import, and it'll just populate that up in my top level assembly I'm working on, or simulation I'm working on. So at this point, they're just regular. They're not parametrically linked. It's just a nice copy from the lower level up top. So you can start to manage these individually and just edit them and make them one-off, whatever you'd like. The other way you can do this is upon the initial creation of the simulation study. Let's say I'm back at a static study. I can click import study features. Click OK, you get that same little pop-up window. To import these things, I click the part that I want to graduate features from, filter anything out, and then import it in. And now you have the mesh controls and you have the foundation bolts, everything you saw earlier on this new study as well. But that's maybe I think 4 years old now, I think 3 or 4 years old, that capability. It's one of the newer ones. But yeah, that's import study features. Any questions? That's the end of my presentation here, ladies and gentlemen. So check out our YouTube channel. I do post my webinars and presentations up there. If you want more content from myself or my colleagues, we post a lot. There's a lot of activity up there. Or if you're a reader, you like to read, check out the blog. But that's it. I'll be around if you guys have questions.